Okay, guys, I guess we're going to start now. So, welcome to week 3 in Challenge Room. This week we're going to be focusing on data structures and algorithms. Should be fun. Okay, so
hmm
firstly, I'm going to ask you guys a question and a kind of like a problem. I want you guys to construct a house, and you guys might have zero experience, a lot of experience in this field, but there are two things that I can give you that you should be able to use to construct this house. One of them is going to be a toolkit. If I give you this toolkit, you should be able to at least think of what you need to build this house. But a toolkit alone cannot build this house. But the second thing I'm going to give you is a 1,000-page manual of like how to build a house. And it's going to tell you step by step on how to like plow the land, build a wall, and like add stairs, add a roof, and all that stuff. And these instructions are going to use the toolkit that I gave you. And with these two things, you should be able to construct this house. It may not look pretty, it may take a lot of time, but you'll still construct the house. And that's the point of this problem. Similarly, in CS, when you're constructing a solution to a problem, you need two things. And those two things are data structures and algorithms. And similarly, um, like, the, like the house example, data structures act like your toolkit, and algorithms act like your instructions. You have to use the data structures in your algorithm, and following the algorithm will eventually lead you to some sort of a solution. These two topics, data structures and algorithms, are fundamental in computer science, and that's why we're thinking of teaching it to you guys so early on in the year. So let's get started with data structures. So there are two main branches. There's the primitive data structures, which should be reviewed for you guys. They're like the integers, the characters, the booleans, those stuff. And then there's the abstract data types. And they're kind of like two kind of subgroups for this. And one of them is like built-in structures. And since I'm going to be showing Python today, they're going to be built-in structures in Python. So like lists, arrays, tuples, sets, dictionaries. Um, but there's some non-built-in structures, and then that's when we use user-defined structures that I make or like we make ourselves. And these are like stacks, queues, linked lists, graphs, and trees. So that's going to be kind of like the agenda for today, and then after that, we're going to be going to algorithms. So I give it to Michelle.
All right, hello. So we're going to talk about primitive data structures for a bit first. All right, so primitive data structures, some examples. So there's integers, and this is all review. You guys should know this already. Integers are numbers without decimals, like 3, 1, -4. There are also floating point numbers, which are called float in Python, or just float normally. There are numbers with floating decimal points, like 3.14. And then there are strings, which is a collection of characters and just words that you put around, you can put quotations around them, usually in code. And continue on. You also have characters, which is a single symbol, like A or the pi symbol, stuff like that. And you have booleans, which is something that can only be in one or two states, true or false. And finally, you have pointers. And you guys learned this in the last lesson. It's, in short, it's an object that stores memory address to another variable, like 0, x1337.
Yeah. Okay, so those are the primitive data structures that should be reviewed for you guys, and abstract data structures, which should be reviewed and some should not be reviewed. So let's get started. So I'm going to be talking about the built-in data structures first. So they're lists, and lists are containers of different objects. So like we have one, the word one, the character A, true, and 3.14. They're all different types. And then we have an array, and arrays are containers of same objects. So everything in an array will have the same data type. So 2, 4, 6, 8, 10. And you might be asking, what's the difference between a list and an array? And I'll show you in the Colab in like 1 minute, but arrays allow you to do numerical operations on multiple objects at once. So let's go in here. So over here we have a list. Wait, can you guys see the Colab? Okay.
Yeah, okay.
Yeah, we can see it.
Okay, that's good. So here's a list. It's 2, 4, 6, 8, 10, like that. And here we have an array. And arrays usually allow us to do multiple operations or one single operation on multiple objects. So for example, let's say I wanted to divide everything in this list by 2. So I kind of want to like make everything from 2, 4, 6, 8 to 10 to 1, 2, 3, 4, 5. And let's see how I would try this with a list. Let me comment this, uncomment that, comment that. And let me just try it out with dividing the whole list by 2. And this will give us an error, and it will say unsupported operand types for list and int. This basically means you cannot do this with a list, and that's where we got to use arrays. And there's a library called NumPy, which is very useful for a lot of stuff in code. And there's one specific module called array, and that allows you to create an actual array. And so if we try this again, but instead of using array, we actually get the array called 1, 2, 3, 4, 5, and it what do you call? It divided everything in this array by 2. And if I put 5 here, it would give me 1, 2, 3, 4, 2.5, and that's divided by 2. And Python recognizes these two as I put type list just to like see what it is as a list and numpy.end array, which is also like an array. Okay, we've done lists and arrays. Now we have tuples, and tuples are collections of objects which are ordered but are immutable. So that means once you create a tuple and you have a value indexed here, you cannot change it. So for example, let's say I had this tuple of 1, 2, 3, 5, 9 in the string 11. Let me just print it so you guys can see how it looks like that. But if I wanted to change the first index of this tuple from 1 to -1, I can't do that because it's immutable, and it'll bring up an error saying tuple object does not support item assignment. And this is the difference between a tuple and a list, because over here in a list, I can easily just change that. I just have to comment this. I can easily just change the first element in this list to 100, and I won't get any errors. But when I do that in a tuple, it'll raise an argument. Okay, those are the first 3. Now we have sets, and sets are a collection of unordered and unindexed objects. And that's basically it. But I'll show you some code representation so you understand. So to create a set, you surround it with curly braces. And also another way you can just kind of do like set, and then you put it in braces and you put a list in there, and it'll automatically get converted into a set. But you can also use curly braces. So I have this set of 1, 2, and 3. And there are 2 main operations that I'll be going over, but like there's more in the Python documentation. If you guys want to see it, you can go ahead. There's add and remove. Basically what add does is it adds it to the set, and remove removes that object from the set. And the cool thing about sets is that sets do not indicate duplicates of values. So over here, I added 4, and then I removed 1, and then our set becomes 2, 3, and 4. But here on this line right here, I add 2 again. But if after I print it, you see there's no like 2's. There's only 1, 2. That's because Python detects that this set already has a 2, and there's no need to actually add another duplicate. Next, we have dictionaries or maps. Dictionaries are containers of unordered, changeable, and indexed objects with keys and values. Over here, we have a dictionary, and this dictionary has multiple keys that point to multiple values. And for example, the key school will point to the value SJM. The key postal code will point to this, N2V, 2V1. And the cool thing about dictionaries is that you can nest dictionaries and dictionaries. So I can have address, which points to a dictionary. And then in this dictionary, it has multiple keys, which point to multiple values. And you might be wondering, how do I access each specific value from a key? So let's say I wanted to get what the value of school was. You can do that by putting the name, the variable DCT or whatever your dictionary is called. And then you can kind of access it like an index, like a list, but instead of putting a number, you would just put the key, and then that will become the school name. And over here, I put the postal code of SGM, which is school name, is the postal code, and I access that through this notation. Um, to access, let's say, our province, you can do what we did before, but instead you have to put another index because it's a nested dictionary. So when I access dict of address, it points to a dictionary which has the key province, and that key province points to Ontario, and then we get the province SGM is in is Ontario. And the cool thing about a dictionary is that you can change some values. So let's say I wanted to change the number or the street number SGM was on from 650 to 101. I can easily do that. And over here, you can see after I print it, it did change. You can also add keys and values to a dictionary. So I added the key's phone number, which points to this long phone number. And it did that. Okay, so those are the built-in data structures that we get from Python. And now I want to talk about user-defined structures. So the structures that we got to make ourselves. And the first one are stacks. Stacks are collections of objects that are inserted and removed by the LIFO principle. And LIFO is just an acronym that says last in and first out. And a nice example of this is when you wash dishes. Let's say you had a plate that's named A, and you would wash it, and then you would put it at the bottom of your stack, and then you would do B, and then you would do C. And after you wash those three plates, you would stack B on top of A, C on top of B. And now you want to dry your dishes. So you take the topmost one, because if you take the bottommost one, the chances of the whole stack falling are high. So you just want to be as careful as you can with your plates. And you take C off, you dry it, you put it in your cupboard. Do the same with B, and then you do the same with A. And this is kind of how the data structure works as well. It's kind of like you add in objects as if they were plates, and you get rid of objects as if you're drying your plate. And an example use case is kind of like the back and forward button on your browser. So every single time it'll keep track of your history and it adds it in the stack like that. So oh wait, I need to go to Colab. Let me show some code representation. So here's a stack. Um, like I said before, it's just a collection of objects, but in a different way. So we can kind of represent it as a list. And I call self.items the amount of items in the stack. And there are two main functions that you really need to know for a stack, push and pop. So push basically means adding a plate on top of your stack, and pop means getting rid of that plate and putting it in your cupboard. And push simply means appending an item to a list. Pop means popping it, so getting rid of the most recent one that you added. And I added some nice functions here. Peek, which basically returns the topmost plate or topmost object, and is empty returns a boolean if the stack is empty or not, and the size of the stack. So let's go through some examples. Here I initialize the stack, and I basically put the plate 1, 2, 3, and 4 in that specific order. So that means when you print out the stack, it's going to look like this, 1, 2, 3, 4. And the size of the stack is 4. And the most important thing here is that 4 was the last element or last object that we added to the stack. That means when we pop it or when we get rid of the element at the top of the stack, we should be getting rid of the element 4. And once we do that, you can see that 4 is gone and it's just 1, 2, and 3. And then we can do stack.peek, which will tell us the element at the top of the stack. And since we got rid of 4, that's going to leave 3. And then, yeah, it's not empty because there's still 3 elements left. And you might be thinking, okay, let's say I wanted to solve a problem that involves stacks. I don't want to write all of this. I don't want to write this class every single time. Well, you can easily do this with just a list. And a nice representation just using a list is instead of using this push method, you can just kind of call it append. And if you remember what an append is, it's just adding an element to an array. And removing the element at the top of the stack is just pop. And just yet again, I just added 5, 4, 3, 2 to the stack. I popped 2 because that was at the top, and then it became 5, 4, 3. And then to peek or find the element at the top of the stack, I just find the -1 index. You guys remember. Yeah, so that's basically stacks. They're useful, and you'll see why later on in the year. But other than stacks, there's something called queues. And queues are collections of objects that are inserted and removed by the FIFO principle. And FIFO is another acronym that's the first in and first out principle. And you can think of this as a line at the movie theaters. Let's say I was in line and then my friend John was behind me. I would be the first one in line. That means I would be the first one getting my ticket. And then after I leave that line, John is going to be the next person in line, and he's going to be the next person out of the line. So a queue is basically a queue in real life too, and as a data structure. And an example of this in real life is when you're resolving simultaneous server requests from multiple clients. So if you have a server set up and you have multiple people around the world pinging the server, it's not all going to come at the same time, right? So you need to kind of organize these requests into a queue, and you just do them one by one. And after you resolve one, you go to the next one, and so on and so forth. Okay, so that's the English definition. Let's look at it in code.
Wait, before you do that, Sammer had a question that said, what
Yeah,
are some uses for stacks?
some uses for stacks. Kind of when some kind of problems, you need to keep track of the most recent that you put in a list. And you can use stacks as if they were lists. Um, the stacks just work like lists, but the main reason you would use a stack, or we call stacks, is because lists have different properties and stacks have different properties. So some specific problems, like an interview or something, will require you to use stack. Yeah.
Nice, thank you.
So the code example that we have here is just another class. And the two functions I want to focus around are enqueue and dequeue. And think of enqueue as someone entering the line, and dequeue as someone leaving the line at the movie theater. And so in order to do this, we do items.insert zero item. So this basically inserts a specific item at the 0th index of our list, and dequeue just pops it out. And I have size and empty just because that's a nice function to have. So I add number 1 to the line, 2 to the line, 3, and then 4 to the line. And this makes number 1 the first person in line, and then number 4 the last person in line. And you can see that in the list like this. Um, yeah. And then when I do dequeue, that basically means the person in line, or like the first person who got in the line, is going to leave. So that means 1's gone. And then it only becomes 432. And then the size is going to change when I dequeue again. It becomes 2, and then I dequeue twice more, and then it's empty. And you might be thinking, okay, I don't want to write that all the time. Well, Python, there's a library called collections, and you can import a module called dequeue. And dequeue is basically a queue. You can use it for a double-ended queue, and we'll get into that later on in the year. But dequeue basically does these two operations already for us. So you can think of enqueuing as append left. So we're appending this value to the left of the list, and dequeuing as just pop. And I add 1, 2, 2, 4 to the line, and this basically means 1's in the first line, first person in line, and then we have the 2's and then 4. And the cool thing about dequeue is that we can count how many times um, uh, an object is in a queue. I could write a function in here too, but it's already built in dequeue, so it's kind of nice. And popping is just like dequeuing. And if, let's say I wanted to add another person into the line, 21 gets added. So yeah, collections is pretty useful. Okay, after queues, this is probably like the last big one, and it's called linked lists. And linked lists are collections of data that contains elements that point to each other. And the elements in this linked lists are a linked list is a node. And there are two main properties in a node. Its value and a pointer. And the pointer points to the next node in the sequence. And a nice analogy I can think of is like if you're on a train and you know boxcars on a train, you can kind of think as the first node in the linked list will be the pilot or like the first I forget what it's called on a train, but like the first ever boxcar on a train. And then that's going to point to the next boxcar, and that'll point to like the passenger boxcar, which points to the storage boxcar, and then it keeps going until there's like no boxcars. And the nice thing about this is that it's very dynamic. So I can add a boxcar in the middle of two boxcars, at the end of a boxcar in the beginning. It doesn't like you have freedom. And there's also a very low memory overhead. And that's because we're sharing the data between every single node. And it's not like a list where all the data is stored by just the list. Um, Linked lists share data. So like this node shares data, which shares data with multiple other nodes. And nodes pointing to other nodes is very important in CS. So here's an example in code. So I made the class node, which basically has two properties like I mentioned before, a value and a pointer. And the value contains the data that we want to store. And next will be the next node in line. And when we're initializing it, we just put none. And then here's the actual linked list. And in a linked list, we usually keep track of the first node. And if we go back to the train analogy, we kind of keep track of the the pilot node, like the pilot boxcar. And we want to keep track of that because if we know which node is in the beginning, we can kind of find out what's the next one and after that, so on and so forth. So I'll go to this function after when we go to add end. So add ahead, what does add ahead do? What does add head do? This basically chains the head node from the one we want it to, um, from the one it previously had. So the previous node is going to get pushed up in the line, and the node that we want is going to become the new head. And this is basically the code that does that. So I change the head node to node, and before I do that, I change and make sure the node.next is self.head node. So it's kind of like inserting in the beginning, kind of like what we did for Q. Uh, yeah. Okay, what does add end do? So in this, I'm gonna go back to this function right here. In def iter, when we iterate through self, what we want to do is we want to keep on going. We want to keep going through every single node that our linked list connects to. So the first node is going to be self.head node, and we want to go through this while loop, which basically says the current node that we're in, we keep doing this until it's not none. And what yield does is it suspends the function execution and returns the yielded value to the caller. So whenever I'm iterating through itself, I'm going to return node as that one value. And then after I'm done that, I'm going to make node next. And then we keep doing that. So I use that in add end. So here I'm adding a node to the end of the entire sequence. So first I check if there's a head node, and if there's no head node, then I make sure that the node that I'm adding becomes the head node. And then in here, I'm just iterating through self, and I'm making the last node in the sequence cur. So after it's done all of that, I keep passing it. I make cur.next the node, and this basically adds the node that we want to the end of the sequence. And you can kind of see that here. Basically, when we initialize the linked list, it's just none. And then comes when we add A, the node A is just going to point to none. And then when we add head of B, it's going to replace A, and then B is going to point to A. And then finally, when we add end of C, it's going to point from B, which points to A, which points to C, which points to none. And that's basically linked lists in a nutshell. And I'm going to quickly go over graphs. And graphs are a nonlinear data structure which contain a finite set of vertices or nodes with a set of pair of vertices called connections. And ordered connections are directed graphs, and unordered connections are undirected graphs. We'll go more into depth of graphs later on in the year, probably like next week or next week. I forget. And trees are just rooted graphs. So there's a new node that's rooted and it basically goes on and on instead of like this where everything's connected. Yeah, and we'll go more in depth later this year. Stay tuned. Yeah, now we're gonna talk about algorithms, and it's over to Michelle.
All right, thank you, Aditya. Okay, so this is also almost important, it's just more review. So input is some data that is given to the algorithm with the intention of using it to accomplish something. So, for example, an algorithm can take the input of 3 numbers, and then after running the algorithm, you get an output. which is the data that exits the algorithm after it is run, and it's usually useful for the user. Like usually the output's what you want. So for example, an algorithm can output the sum of the three numbers that have been inputted. And oh my gosh, I don't know how to pronounce this. Definiteness. It means that each step of the algorithm must be definite and there are no exceptions to the rule in order to ensure that the algorithm runs smoothly for all cases and that it doesn't break. All right, continuing on. Finiteness is the characteristic that defines that the algorithm must end after a certain number of steps. So it can't run forever. It should end at some point with a useful output. And effectiveness, which states that each step of the algorithm must be simple enough to be performed in a reasonable amount of time and correctly. So basically how just it has to be effective. Yeah.
All right. So Michelle went over the important parts of the algorithm, and I'm just going to go over some examples. So I'll talk about searching algorithms like linear search and binary search and compare them. So yeah, you're given a list and you want to find element X and return an index. So the first approach that you all might know and remember, or just it's kind of like naive, I guess, is linear search. And the algorithm here is basically you loop through every single element in an array or a list, and you basically, until you find the element you're looking for, you never stop. So you keep going until you find it. And if you never find it, then you know it's not on the list. And you keep track of where you're at. So we do that by setting a variable like I to 1. And then we just check if the current position we're at is equal to the element we're looking for. And if we are, then we basically just print the element and we end the program. Some pseudocode right here. And so basically, for each item in the list, if match item is equal to value, then return the item's location. And then that's basically it. And then if you remember from the first week, it's just a simple for loop. So the time complexity will run O of n from the worst case that the value that we're looking for is at the end of the list. Okay, that's linear search. I'll just show some Python code right here. So yeah, we have an array, right? We were looking for element. We loop through the array for I in range, the length of the array. And if that element is equal to the element we're looking for, then we return I. And if it's not, and we never pass that if statement, then we return -1. And over here we have a test case, and we're looking for the element kiwi, and then our program, we run it, and it says the element kiwi is found at index 4. We can check 0, 1, 2, 3, 4. So yeah, basically what it did is that it looped from apple to banana and then cherry, and it kept checking until it met something called kiwi, and then it found kiwi, and then that was it. So O of n is it's kind of fast, but we can do better than that. And here's a pseudocode for something we call binary search. And I don't really like the pseudocode because it's just pseudocode and it's kind of like messy, but I'll try my best to explain it as simple as it can be. So basically you want to keep track of 3 things, but before that you need to make sure that the array that you're trying to search is sorted. That's very important. So whatever element that you're looking for in a certain array, the array has to be sorted. N is going to be the size of the array, and X is going to be the value we're looking for. And the 3 values that we have to keep track of is the lower bound, the upper bound, and the midpoint. And so basically, I really don't like the pseudocode. I might just go to the code. The code looks better. Basically, what I do is I know my low, my high, and my mid. And I keep repeating this while loop until my low is less than or equal to, until my low is greater than my high. So this basically means if my upper bound ever becomes lower than my lower bound, like I should stop because that makes 0 sense, right? Because you can't have your maximum value to be smaller than your minimum value. That just makes no sense. So I keep doing that until like that edge case happens. And what binary search does is it splits the list until kind of like compares like where you are in the list. So it's kind of hard to explain just out of the blue, but here, look. Mid is basically every single time we iterate, it's just going to be the midpoint. So like low plus high divided by 2. Um, and over here, this if statement, if array of mid is less than the element. So this means if the element that we're looking for is greater than the middle of the array. And if that's true, then we have to change our lower bound to become middle. And the reason this is going to work is because our array is sorted in the first place. And since the array is sorted, we can kind of make this operator right here, less than or equal to, less than or greater than, we can kind of make these operations and it's not going to like run wild. It makes sense because um, if it's greater than the middle element, then we kind of have to get rid of everything that's smaller than the element. And we do the opposite here. So if the element is smaller than the one in the middle, we change the high to the middle. And when array of mid is equal to element, we basically return the middle. So I kind of want to go to the example because the example is really good. So I have a list right here: apple, banana, cherry, kiwi, mango, melon, orange. And this is sorted, by the way. So we know this is going to work. So the way it's going to work, let's say our element that we're trying to find is melon. Okay, so the lower bound is going to be 0. So it's going to be apple right here. The upper bound is going to be orange. And the middle of the whole list is kiwi. So when we start off, we're going to see if kiwi is less than melon. And kiwi is less than melon. This doesn't make sense. I should have done it with numbers, but I just wanted to show that you can kind of compare um, words with words. It just checks if k is before m, and k is before m. So this basically means we change the lower bound to mid plus 1. And since this was mid, it basically it gets rid of this entire part of the list. That whole left part of the list doesn't matter to us anymore. We don't care about it. And now we do this again. So we check the middle. It's melon.
Hey, Aditya.
Yeah.
Pause for a quick second. I just want to say attendance is open. It's in the announcement channel. If for whatever reason the bot doesn't message you, send mention that in like general or something like that, and I can log you manually.
But don't do the attendance yet because the lesson isn't over. So
It's almost
They
over.
can do the it has to be open before they leave. So I mean,
yeah,
Yeah.
yeah, okay, sure.
You can
do
still
it,
fill
but
out the attendance.
pay attention still.
But still, yeah, still
Yeah.
pay attention. Okay, back. So back where we are, we basically got rid of the left part of this list because we don't care about it anymore. And the element that we're still trying to find is melon. And over here, melon is in the direct middle of the list. And we found it, right? Because that's basically where melon was. And we return the middle of this list, which is calculated by the low and the high divided by 2. And that's index 5. And if we go back to the original list and we count it out, 0, 1, 2, 3, 4, 5, that's correct. And you might be thinking, okay, we did a lot of code, um, more than linear search, but how did this help us? Like, it's probably not even that fast. Well, now we got to measure the time complexity of this. And the one question I want to ask you guys is how many times can you divide by n by 2 until you have 1? And what this question kind of means is when you're doing a binary search, you're always splitting this list by 2. And every single time you split it by 2, you're making the search area smaller. And you keep doing this until the search area is 1. And the reason you do that is because the search area is 1, that means you found the element. And that's the index of it. And you basically want to find the worst case scenario. And if you kind of did the math, it's basically 1 is equal to n over 2 to the power of x. And you can kind of reformat it. But x really means how many times we're going to split this list by 2. So how many times we're going to divide this or like split the list. And every single time we do that, we're going to add 1 to x. So x is just going to be the amount of times we split the list in 2. We multiply 2 to the power of x by both sides. We do some math. We do log 2 of both sides. And then we do the power rule. And we log 2 of 2 is just 1. And then we get x is equal to log 2 of n. And that basically means the time complexity of binary search, in the worst case, is O log of n. And if you know math, log of n is faster than O of n. Log of n is faster than n. And that's pretty good, right? Because once you get to larger parts larger lists and stuff, linear search is going to take a long time. Because let's say you had like a 1,000 element list, and the element you're looking for is all the way at the end. That's going to take a lot of time, or like more time than it should. But binary search reduces that time by log of n, so a log of 1,000. So it's really good. And I guess that's kind of the conclusion to today's lesson. And I just want to say this again. Understanding data structures and algorithms are very important. And I hope that today's lesson kind of gave you guys a view of what computer science is like with these two topics.
And also, can I also add that for the binary search, if you ever take Mr. Chapman's grade 12 computer science course, which I hope all of you guys do, he actually does a lesson on this, and the way he explains it is actually really well. So I want to just explain it like that. So basically what he did was, so say you want to find a word in a dictionary. So you look at the middlemost word, and that's like just in the middle of the alphabet, and you look at the word and you see if that word is before or after the word you're looking for. And then okay, so say you're looking for xylophone, and the middle word is, say it's like melon or something, and you know that xylophone comes after melon in the alphabet. So in that case, you take the entire first half of the dictionary and you just cut it out. And he actually shows you an example where he just like cuts the entire book in half, and it's really funny. But yeah, you just cut it out, and then you do the same thing. So you find the middle, and then figure out where the word is in relation, which half it is in, and then you cut out the other half. So I just stated what Aditya just explained, but in my head, it makes more sense that way in a more physical
Does he really cut the
representation.
book in
So
half?
yeah, yeah, he does. No,
Oh,
he showed us a YouTube video. He has like a knife and stuff.
damn.
I actually have a screenshot of it. I
Check
can
the meme
drop
in
it
the
in
memes
after.
channel. There's a meme in the
yeah,
memes channel. I show us doing it.
I'll drop it in. Hold on. But yeah, Aditya, you can keep on talking now if you want.
Yeah. So yeah, that's basically it for today's lesson. I'm gonna stop recording on OBS.